Welcome back. So we're still talking about the chapter Incline on pericyclic reactions, and the last topic in that chapter covers uv-Vis spectroscopy and color. Okay, so here we see the energy gap for a 4-atom pi system, where each of those atoms has donated 1 electron to that pi system, and therefore we have 4 molecular orbitals formed, and 2 of those are occupied. The highest occupied molecular orbital is psi2, so if we add the right frequency of light, we can promote one of those electrons to psi3, and that becomes our highest occupied molecular orbital. But if we have a more conjugated system, then what we see is that it actually takes less energy to promote an electron, because these energy gaps become closer and closer together the more conjugated the bonds are. Now, I'm not going to cover all of this information for my class because I just want to cover what I feel like is the most important information here. Okay, so you can see here, if we have 2 double bonds, then our lambda max is going to be about 217 nanometers. 3 double bonds is going to make our lambda max around 258, and 4 double bonds about 290. So our lambda max gets longer and longer and longer according to how many conjugated double bonds we have. Now you can actually calculate what that lambda max would be if you know all of the things that are connected to our overlapping pi system, our conjugated pi system. For example, you're going to add 30 nanometers for each additional double bond, 5 for each methyl group or alkyl group, and then if you have a double bond outside a ring or inside a ring, it's going to vary like that. So you can actually calculate what your lambda max would be, and there are programs that can do that for you. I'm not going to test you on that, but what I want you to be able to understand is which molecule would have the longer lambda max. So in other words, which one has more conjugated double bonds? Okay, and so that's not part of that homework set, so we won't work that homework set. But notice here that we have so many conjugated double bonds in a molecule like lycopene or beta carotene that these are actually in the visible region, which is 400 to 700 nanometers. These can actually be seen. So lycopene and beta carotene are red and orange because they have so many conjugated double bonds that actually drags them into the visible region. Okay, so beta carotene absorbs blue light, and this is the wavelength that it absorbs, and so we're going to see that as red or orange. Okay, so if we can break that conjugated pi system, then we can actually make those chromophores no longer visible. So something like bleach will break those double bonds and actually make them not visible. So bleach doesn't actually remove these things from your clothing. It actually just breaks the double bonds so you can't see them anymore. So the problem set that I want to work here is to ask you which of these species would actually have the longest lambda max. And I think that problem set is actually not in the last not in the newest edition of the book. So I'm going to go ahead and work it here. So which of these has the largest lambda max? And this is what I consider to be important for my class. Okay. So I'm going to draw 3 of these bicyclic systems, and see if you can tell me which one has the larger lambda max. Okay, so now we have A, B, and C. Which has the larger lambda max? Well, notice that for A, all of these are conjugated. There are no sp3 hybridized carbons between those double bonds. Okay, what about B? Well, this is an sp3 hybridized carbon, so all three of these are not conjugated. And here we have C, where we have an sp3 hybridized carbon here. So A is going to have the larger lambda max, okay, because it has more conjugated pi bonds. Okay, and that's all I wanted to cover for my students for the chapter on pericyclic reactions from Klein. And thanks for listening. I'll see you next time.